Hello, and welcome. I'm so glad you're here. If you've arrived at this moment feeling tired, or restless, or simply in need of something gentle to carry you towards sleep, then you've come to the right place. There's no need to do anything at all right now. You don't need to remember facts, or take notes, or even keep your eyes open. All you need to do is let yourself settle in, breathe slowly, and allow your mind to drift wherever it wants to go. Tonight, we're going to explore something truly special. We're going to wander together through the quietest corners of science, the places where nothing makes a sound, where silence itself becomes a kind of presence. We'll visit phenomena so still, so hushed, that they seem to exist outside of time. And yet, within that silence, entire worlds unfold. Stars are born without fanfare. Cells communicate in whispers too soft for any ear. Mountains rise grain by grain, and light travels through the vacuum, carrying stories across billions of years, all without uttering a single word. If you enjoy this kind of gentle journey, you're welcome to follow along for more. But there's no pressure at all. Just rest. Just listen. Just be. Let's begin slowly and softly with the most silent place we know. Space, that vast ocean beyond our atmosphere, is the quietest environment in the entire universe. Sound, as we experience it, requires a medium to travel through, molecules of air or water or solid matter that can vibrate and carry waves from one place to another. But in the vacuum of space, there are so few particles that sound simply cannot exist. If you could somehow survive in the emptiness between stars, you could scream as loudly as you wanted, and you would hear nothing, not even an echo. The silence is absolute, unbroken, eternal. And yet, space is far from empty in other ways. Light moves through it freely, carrying information across unimaginable distances. Electromagnetic waves ripple outward from stars, pulsars, and galaxies, painting the universe in frequencies we can detect but never hear. It's a kind of silent symphony, a concert played entirely in wavelengths that bypass our ears and speak directly to our instruments, our cameras, our curious minds. When astronauts float outside their spacecraft, they report a profound sense of quiet. Even though their radios crackle with voices from mission control, even though their own breathing sounds loud inside their helmets, they can see the Earth turning below them, storms swirling, oceans gleaming, cities glowing, all in perfect, utter silence. It's a perspective that changes people. The stillness of space, they say, makes you feel both infinitely small and deeply connected to everything. Deep beneath the surface of our own planet, there are places almost as quiet as space. In caves that wind far from the reach of wind, water, and human noise, the silence becomes thick, almost tangible. Explorers who venture into these subterranean chambers often describe the experience as disorienting. Without sound to anchor them, their sense of space begins to blur. The darkness and the quiet merge into a single sensation, a kind of sensory emptiness that can feel both peaceful and overwhelming. In some of these caves, the only sounds are the occasional drip of water, each drop falling through the stillness and landing with a soft, isolated plink that echoes for a moment before fading back into nothingness. These drops, falling one by one over thousands of years, are the architects of the cave itself. They carry dissolved minerals, calcium carbonate mostly, and as each drop evaporates or flows away, it leaves behind a microscopic layer of stone. Slowly, imperceptibly, stalactites grow downward from the ceiling, and stalagmites rise from the floor, all in silence, all without hurry. The process is so gradual that a single stalactite might grow only a few millimeters in a human lifetime. And yet, given enough time, these silent drops create cathedrals of stone, vast chambers adorned with delicate formations that look like frozen waterfalls. curtains of calcite, forests of slender columns. The cave becomes a monument to patience, a testament to the power of small, quiet actions repeated endlessly. There's something deeply soothing about that, isn't there? The idea that monumental change doesn't require noise or force. That beauty can emerge from the gentlest of processes, one drop at a time, one moment at a time, without any rush at all. Glaciers, too, are monuments to silent transformation. These rivers of ice move so slowly that you can stand on one and feel no motion whatsoever. And yet, beneath your feet, the glacier is flowing, creeping downhill under its own immense weight, grinding rock into powder, carving valleys that will shape the landscape for millennia. The ice moves perhaps a few centimeters a day, sometimes less, sometimes a bit more, but always without fanfare, always in a hush. Inside a glacier, the world is blue and still. Light filters through the ice, scattering in such a way that longer wavelengths are absorbed, and only the shortest, the blues, reach your eyes. It's a cold, serene glow, like being inside a frozen dream. The ice itself is ancient, formed from snow that fell centuries or even millennia ago. Each layer compacted by the weight of the layers above, each bubble of air trapped and preserved, holding a tiny sample of the atmosphere from another time. Scientists drilled deep into glaciers to extract cores of ice, and within those cores, they find a silent record of Earth's climate. The composition of the air bubbles, the isotopes in the water molecules, the dust and pollen trapped within, all of these speak to conditions long past. It's a library written in ice, a history told without words, waiting patiently to be read. And as the glacier moves, it carries this history with it, slowly, quietly, until one day, far downstream, the ice reaches a place warm enough to melt. The water flows away, joining rivers and oceans, and the ancient air trapped inside is released, rising into the sky, rejoining the atmosphere after centuries of silence. Beneath the ocean, there are regions of profound stillness. In the deepest trenches, miles below the surface, the water is cold, dark, and nearly motionless. The pressure is so immense that it would crush most creatures instantly, and yet life persists, adapted to conditions that seem impossibly harsh. The animals that live here move slowly, conserving energy in an environment where food is scarce and every calorie counts. The deep sea is not entirely silent, of course. Whales sing, shrimp snap their claws, and the hum of distant ships penetrates even to these depths. But there are moments, vast stretches of time and space, where the water is still and quiet, where the only motion is the gentle drift of marine snow, tiny particles of organic matter falling slowly from the sunlit surface above, tumbling down through the darkness like a soft, endless rain. This marine snow is the primary source of food for deep-sea creatures. Each flake is a fragment of life from above, a piece of a dead plankton, a bit of fecal matter, a sliver of a jellyfish. As it falls, it's consumed by organisms at every depth, a quiet transfer of energy from the bright world above to the shadowed world below. The journey can take weeks, and by the time a particle reaches the ocean floor, it has been picked over, broken down, and transformed, but it still carries with it a whisper of sunlight, a memory of the surface. On the ocean floor itself, in some places, there are fields of manganese nodules, strange potato-shaped rocks that grow slowly in the sediment. They form around a tiny nucleus, a shark's tooth perhaps, or a fragment of shell. And over millions of years, layers of metal oxides precipitate out of the seawater and coat the nucleus, building the nodule outward, molecule by molecule. The process is so slow that it makes the growth of stalactites seem rapid by comparison. A nodule might grow a few millimeters every million years. And yet, across the abyssal plains, these nodules lie scattered in their millions, silent witnesses to the passage of deep time, each one a small, patient miracle of geology. There's a certain comfort in contemplating such slowness, such quietude. In our daily lives, we're surrounded by noise and haste, by the pressure to move quickly, to respond instantly, to keep pace with a world that never seems to stop. But the natural world, in so many of its processes, reminds us that not everything needs to hurry, that some of the most profound changes happen slowly, quietly, without any need for attention or applause. Consider the way a seed germinates. You plant it in soil, water it, and then you wait. For days, sometimes weeks, nothing visible happens. The seed lies in the dark earth, silent and still. But inside, a transformation is underway. The seed absorbs water, swelling, softening. Enzymes activate, breaking down stored starches into sugars. Cells begin to divide. A tiny root emerges, pushing downward into the soil, anchoring the future plant. Then a shoot unfurls, reaching upward toward the light. All of this happens without sound, without drama. The seed doesn't announce its intentions. It simply does what it has been designed to do, quietly, patiently, in its own time. And when the shoot finally breaks through the surface of the soil, it's a small, humble event, easily overlooked, and yet it represents one of the most fundamental acts in the living world, the beginning of a new life. Plants, in general, are masters of silent growth. A tree adds a new ring each year, a thin layer of wood that encircles the trunk, marking the passage of time. In a good year, with plenty of water and sunlight, the ring is wide. In a difficult year, it's narrow. But always the growth is quiet. You can sit beneath a tree for hours, days even, and you'll never hear it growing. You'll never see it happening. And yet it is, constantly. Cells are dividing, walls are thickening, sugars are being transported from leaves to roots, water is being pulled up from the soil through microscopic channels, all in a silent, intricate dance of chemistry and biology. Over decades, that silent growth transforms a sapling into a giant. A tree that was once no taller than your knee becomes a towering presence, a living column that can support entire ecosystems. Birds nest in its branches, insects burrow into its bark, fungi connect to its roots underground, forming networks that allow trees to share nutrients and even chemical signals. It's a community built on quietness, on slow, steady cooperation. The mycelial networks beneath a forest floor are particularly fascinating. Fungi send out thread-like hyphae that weave through the soil, connecting tree roots to one another in what scientists sometimes call the wood wide web. Through these connections, trees can transfer sugars, nitrogen, and other resources. A large, healthy tree might support a younger, smaller tree growing in its shadow, sending it nutrients through the fungal network. It's a form of communication and cooperation that happens entirely underground, entirely in silence, entirely out of sight. These networks can be vast, spanning acres of forest, linking hundreds or even thousands of trees. The fungi benefit too, receiving sugars from the trees in exchange for helping them access water and minerals. It's a partnership millions of years old, a relationship so deeply embedded in the life of forests that most trees cannot survive without their fungal allies. And yet, for most of human history, we had no idea this was happening. We walked through forests, admiring the trees, listening to birdsong and rustling leaves, completely unaware of the silent, invisible web of life pulsing beneath our feet. Science has a way of revealing these hidden worlds, of showing us the quiet miracles that surround us. And often, the most profound discoveries are the ones that happen in silence, in the careful observation of things that don't shout for attention. Take, for example, the way light travels. Photons, the particles of light, move through space at a constant speed, roughly 300,000 kilometers per second. They do this without effort, without friction, without sound. A photon emitted by a distant star might travel for thousands of years, crossing the empty gulf between galaxies, before finally arriving at Earth and entering your eye or a telescope's detector. It carries information about the star that created it, encoded in its wavelength, its energy, its direction, and it delivers that information silently, effortlessly, after a journey that spans both space and time. When you look up at the night sky, you're seeing the universe not as it is now, but as it was. The light from the nearest star beyond our sun, Proxima Centauri, takes about 4 years to reach us. The light from more distant stars takes longer. Some of the stars you see might not even exist anymore. They might have exhausted their fuel and collapsed, or exploded in supernovae, but their light is still traveling toward us, still carrying the image of what they once were. It's a humbling thought, and a peaceful one. The universe is so vast, and light's so patient, that the past and present mingle in the night sky, all without a whisper. Even here on Earth, light plays silent roles that shape our world. Photosynthesis, the process by which plants convert sunlight into chemical energy, is one of the most important phenomena in the history of life. It happens in the chloroplasts of plant cells, in structures called thylakoids, where pigments like chlorophyll absorb photons and use their energy to split water molecules. The process releases oxygen as a byproduct, and that oxygen, over billions of years, has transformed Earth's atmosphere, making it breathable for animals like us. Every breath you take is a gift from plants, from their quiet, tireless work of capturing sunlight and turning it into life. And it all happens in silence. The leaves don't hum or buzz as they photosynthesize. They simply do it, moment by moment, as long as the sun shines. There's a beautiful symmetry to it. The sun, a massive ball of fusing hydrogen 93 million miles away, pours energy into space in all directions. A tiny fraction of that energy reaches Earth, and an even tinier fraction is captured by plants. But that tiny fraction is enough to power nearly all life on the planet. It's a chain of silent gifts. The sun gives light, plants give oxygen and food, and animals, including us, give carbon dioxide back to the plants. Around and around it goes, a cycle as old as complex life itself. Crystals, too, grow in silence. When a solution is saturated with a mineral and the conditions are just right, molecules begin to arrange themselves in orderly patterns. Atom by atom, layer by layer, the crystal builds itself, following the geometric rules encoded in the properties of its constituent elements. Salt crystals form perfect cubes. Quartz grows in hexagonal prisms. Snowflakes, which are ice crystals, develop intricate, branching patterns, each one unique, each one a small work of art created by the interplay of temperature, humidity, and physics. No two snowflakes are exactly alike, or so the saying goes, and while it's impossible to verify that claim absolutely, it's very likely true. The number of possible arrangements of water molecules in a snowflake is so astronomically large that the odds of two identical flakes forming are vanishingly small. And yet, despite their uniqueness, all snowflakes share certain symmetries, certain patterns, because they all follow the same underlying rules. They fall from the sky in silence, drifting on the wind, tumbling gently through the cold air. When they land, they might melt immediately, or they might pile up with billions of others, forming a blanket of snow that muffles sound and transforms the landscape into a soft, white stillness. Snow has a particular quality of quiet. It absorbs sound waves, trapping them in the spaces between the flakes, so that a snow-covered world feels hushed insulated, as if the earth itself is holding its breath. Walking through fresh snow, you notice the absence of echoes, the way your footsteps sound muffled and close. It's a peaceful feeling, a sense of being cocooned in softness. Avalanches, by contrast, are anything but quiet, and yet the conditions that lead to them develop in silence. Snow accumulates on a mountainside, layer upon layer, each layer bonding to the one below, or sometimes failing to bond properly. Weak layers can form, planes of instability where the snow might slip. The mountain holds this tension quietly, invisibly, until something triggers the release. A sudden temperature change, a gust of wind, the weight of a skier passing overhead. Then, in an instant, the silence breaks and thousands of tons of snow roar downhill. But before that moment, there's only stillness. The mountain stands, the snow rests, and nothing announces the danger. It's a reminder that silence can hold many things, not just peace, but also potential, energy waiting to be released. Volcanoes, too, can be deceptive in their quietness. Between eruptions, a volcano might sit dormant for years, decades, even centuries. Forests grow on its slopes, animals make their homes in its shadow, and people might forget that it's a volcano at all. But deep beneath the surface, magma moves, rising slowly through cracks in the Earth's crust, accumulating in chambers, building pressure. Gases dissolve in the molten rock, and as the magma rises and the pressure decreases, those gases begin to come out of solution, forming bubbles, increasing the pressure further. All of this happens in darkness and silence, miles below the ground, where no one can see or hear. And then, one day, the pressure becomes too great and the volcano erupts. But the eruption itself is just the final, dramatic moment in a process that has been unfolding quietly for a very long time. Geologists study volcanoes by listening to them, not with their ears, but with seismometers that detect tiny vibrations in the earth. Before an eruption, magma moving underground can cause small earthquakes, tremors too faint for humans to feel, but clear in the data. It's a kind of silent language, the earth speaking in vibrations, and scientists have learned to interpret it, to read the signs, and sometimes predict when an eruption might occur. The earth itself is always in motion, always changing, almost always silently. Tectonic plates drift across the surface, moving a few centimeters a year, about as fast as your fingernails grow. They collide, pull apart, slide past one another, and in doing so, they build mountains, open ocean basins, trigger earthquakes. But the motion itself, the slow crawl of continents, is something you could never perceive directly. You need to watch for millions of years to see a continent move from one side of the globe to another. And yet, it happens. India, once an island continent, drifted north and collided with Asia, crumpling the crust and pushing up the Himalayas. The Atlantic Ocean widens each year as the Mid-Atlantic Ridge spews out new seafloor, pushing the Americas away from Europe and Africa. These are changes on a scale so grand, so slow, that they seem almost unreal. And yet they are as real as anything, written in the rocks, recorded in the magnetic stripes on the ocean floor, visible in the fit of the continents if you look at a map and imagine them sliding back together. Plate tectonics is driven by heat from the Earth's interior, heat left over from the planet's formation, and heat generated by the decay of radioactive elements deep in the mantle. That heat creates convection currents, loops of rising and sinking rock that flow like a liquid, though on timescales of millions of years. It's a slow, silent engine that has been running for billions of years, reshaping the surface of the planet, recycling crust, driving the evolution of life by changing climates and creating new habitats. Without plate tectonics, Earth would be a very different place. There would be no mountains, No earthquakes, no volcanoes. The surface would be geologically dead, unchanging, and life, if it existed at all, would have far fewer opportunities to diversify and adapt. It's strange to think that something so fundamental to our world, something that has shaped the very ground we stand on, operates entirely beyond our senses, entirely in silence. The same is true at the smallest scales. Inside every cell in your body, a vast array of molecular machines is working constantly, silently, to keep you alive. Proteins fold into precise shapes. Enzymes catalyze chemical reactions. Ribosomes assemble new proteins based on instructions from DNA. Mitochondria generate energy. Membranes regulate what enters and exits the cell. It's a bustling, intricate world, and yet it makes no sound. The molecules are too small, their movements too subtle to create vibrations we could hear. Even if you could shrink down and enter a cell, you wouldn't hear the whir of motors or the click of reactions. You'd witness a kind of choreographed dance, molecules bumping into each other, binding, releasing, changing shape, all driven by thermal energy, by the random jitter of heat. And yet, from this silent molecular chaos, order emerges. Cells grow, divide, communicate. Tissues form, organs develop, organisms live and breathe and think. You, right now, listening to these words, are the product of trillions upon trillions of silent molecular events, all coordinated, all contributing to the whole. Your heart beats, your lungs expand, your neurons fire, and none of it makes a sound at the level where it's actually happening. The sound of your heartbeat is just a side effect, the vibration of muscle and blood, not the electrochemical signals that trigger the contraction. The sound of your breath is air moving through tubes, not the gas exchange happening in your alveoli. The sounds of your body are echoes, secondary phenomena, while the true work happens in silence. Even your thoughts are silent. The electrical impulses that travel along your neurons, the release of neurotransmitters across synapses, the patterns of activity that somehow give rise to consciousness, none of it produces sound. Your inner voice, the one you might be hearing right now as you listen to these words, is a kind of illusion, a mental construct. The brain activity that underlies it is as silent as everything else. It's a profound and perhaps slightly eerie realization that the mind, the seat of your experience, the thing that feels most intimately you, operates in complete and utter silence. But there's something comforting about it too. The silence of the body, the silence of cells and molecules, is a kind of competence, a sign that things are working as they should. When the body is healthy, it hums along quietly, efficiently, without drawing attention to itself. It's only when something goes wrong that we become aware of it. That pain or discomfort breaks the silence and demands our attention. In a way, silence is the baseline of existence, the natural state of most things. Sound is the exception, the disruption, the event. And perhaps that's why silence can feel so restful, so restorative. It's a return to the baseline, a chance for the nervous system to relax, for the mind to stop processing threats and surprises, for the body to simply be. The universe began in silence, too, or something very much like it. The Big Bang, despite its name, was not an explosion in any conventional sense, and it certainly didn't make a sound. There was no air, no medium for sound waves to travel through. There was only space itself, expanding, and energy cooling, and particles forming. In the first moments after the Big Bang, the universe was unimaginably hot and dense, a seething plasma of quarks and gluons. As it expanded and cooled, protons and neutrons formed, and then, a few minutes later, the first atomic nuclei, hydrogen, helium, a trace of lithium. But it took another 380,000 years for the universe to cool enough for electrons to combine with nuclei and form neutral atoms. Before that moment, photons couldn't travel far without scattering off free electrons. The universe was opaque, a glowing fog. But when atoms formed, the fog cleared. Photons were suddenly free to travel through space, and the universe became transparent. Those photons are still traveling today, stretched by the expansion of the universe into microwaves, forming what we call the cosmic microwave background. It's the oldest light in the universe, a faint glow that fills the sky, invisible to our eyes but detectable by radio telescopes. It's a silent echo of the moment the universe became clear, a relic of a time before stars, before galaxies, before anything we would recognize. Astronomers study the cosmic microwave background to learn about the early universe, to measure its age, its composition, its geometry. Tiny fluctuations in the temperature of the background, variations of only a few millionths of a degree, reveal the seeds of structure, the slight overdensities that would eventually grow into galaxies and clusters of galaxies. It's a map of the infant universe, written in light, preserved in silence for nearly 14 billion years. From those tiny seeds, gravity did its slow, patient work. Overdense regions pulled in more matter, growing denser still, while underdense regions emptied out. Gas collapsed into clumps, heating as it fell inward, until finally, in the densest cores, the temperature and pressure became high enough for nuclear fusion to ignite. The first stars were born. These early stars were different from the sun. They were made almost entirely of hydrogen and helium, with virtually no heavier elements. Because heavier elements didn't exist yet, they were massive, hot, and short-lived. They burned through their fuel quickly, and when they died, they exploded as supernovae, scattering newly forged elements into space. Carbon, oxygen, nitrogen, iron, all the building blocks of planets and life. Those explosions were cataclysmic, releasing more energy in a few seconds than the sun will emit in its entire lifetime. And yet, in the vacuum of space, they made no sound. The shock wave that ripped through the star, the expanding shell of gas and debris, the intense radiation, all of it propagated in silence, visible across light years, but inaudible, a spectacle for the eyes, not the ears. Over billions of years, generations of stars lived and died, each one enriching the cosmos with heavier elements. Gas clouds, now laced with carbon and oxygen and silicon, collapsed to form new stars and, around those stars, planets. Our own solar system formed this way about 4.6 billion years ago, from a cloud of gas and dust that was itself the remnant of earlier stars. The process was gradual, silent. The cloud began to spin, flattening into a disk. Most of the mass fell into the center, forming the sun. In the disk, dust grains stuck together, forming pebbles, then boulders, then planetesimals, and finally planets. Collisions were common, violent even, but in the vacuum, they made no sound. Worlds smashed into each other, merged, broke apart, all in eerie silence. Earth itself was forged in this chaos. A Mars-sized body, sometimes called Theia, collided with a young Earth, and the impact was so powerful that it melted both worlds, ejecting a huge amount of debris into orbit. That debris coalesced to form the Moon. It was one of the most violent events in Earth's history, and it happened without a whisper. The Moon has been our companion ever since, drifting slowly away from Earth at a rate of about 3.8 centimeters per year. Tidal forces between the Earth and Moon cause this gradual separation. The Moon raises tides in Earth's oceans, and the friction of those tides slows Earth's rotation, transferring angular momentum to the Moon, which moves into a higher orbit. It's a slow, silent exchange, a dance that has been going on for billions of years and will continue for billions more. One day, far in the future, the moon will be so far away that it will no longer appear to cover the sun during an eclipse. The perfect alignment we enjoy now, where the moon's disk almost exactly matches the sun's, is a temporary coincidence, a gift of this particular moment in cosmic history. Eventually, the moon will drift beyond that point, and total solar eclipses will become impossible. But that's a concern for a future so distant it's hard to imagine. For now, the moon hangs in our sky, pulling the tides, lighting the night, and doing so in silence, as it always has. And in the quiet spaces between heartbeats, something extraordinary happens that you never hear. Your blood cells are tumbling through vessels so narrow they must fold themselves to pass through, squeezing and sliding in absolute silence. Millions of these soft, flexible discs are moving through capillaries thinner than a human hair at this very moment, delivering oxygen to every corner of your body without making the slightest whisper. The entire journey, from heart to fingertip and back again, unfolds in a hush so complete that even the most sensitive instruments placed against your skin cannot detect the passage of individual cells, only the gentle pulse of pressure that moves them along. The northern lights dance across polar skies in total silence, though many who witness them swear they hear crackling sounds. Scientists now believe these rare acoustic phenomena, when they occur at all, come not from the aurora itself, but from electrical discharges much closer to the ground, perhaps in the air just above the observer's head. The aurora itself, that breathtaking curtain of green and violet light rippling across the darkness, makes no sound whatsoever. It is born when charged particles from the sun collide with oxygen and nitrogen molecules high in our atmosphere, 60 to 200 miles above the Earth's surface. Each collision releases a photon of light, and billions of these silent interactions create the shimmering display. The entire performance unfolds in the near vacuum of the upper atmosphere, where air is far too thin to carry sound waves, and so the lights dance in a silence as deep as space itself. Crystals grow in caves and caverns with a patience that makes mountains seem restless. In certain limestone chambers, calcite formations called cave pearls develop grain by grain, molecule by molecule, as mineral-rich water drips onto a tiny nucleus, perhaps a sand grain or fragment of shell. The pearl rolls slightly with each drop, and over centuries, it becomes round and smooth, growing in concentric layers like a tree. Some cave pearls take 10,000 years to reach the size of a marble. The process is so slow, so quiet, that if you sat in the darkness and listened for a century, you would hear only the occasional plink of water, never the actual accumulation of stone. The pearl itself grows in the intervals between drops, in the silent moments when water evaporates and leaves behind its cargo of dissolved minerals, building the sphere atom by atom in the perfect hush of geological time. Deep beneath the ocean floor, in layers of sediment that have not seen light for millions of years, bacteria lie dormant in a state that barely qualifies as life. These microorganisms, buried under hundreds of feet of mud and sand, have slowed their metabolism to almost nothing, existing in a kind of living pause. They do not move, do not reproduce, do not even repair their DNA with any frequency. Yet they're not dead. Scientists have revived bacteria from sediments more than 100 million years old, organisms that were buried when dinosaurs still walked the earth. In that unimaginable span of darkness and pressure and cold, these cells waited in absolute silence, their biochemistry ticking over so slowly that a single generation might span millennia. They remind us that life can be not only resilient, but patient beyond human comprehension, capable of waiting out entire geological eras without sound, without motion, in a stillness so profound it approaches the eternal. The expansion of the universe happens in perfect quiet, though it is the largest motion we know. Every galaxy beyond our local group is moving away from us, and the farther away it is, the faster it recedes. Space itself is stretching, carrying galaxies along like raisins in rising bread dough, and this expansion has been underway for nearly 14 billion years. You might imagine such a colossal process would generate some cosmic rumble, some deep vibration that resonates through existence. But there is no medium to carry such a sound. The vacuum between galaxies is so empty that even the faint hiss of hydrogen atoms colliding is rare beyond measure. And so the universe grows larger in silence, its galaxies drifting apart in the dark, their lights stretching into the red end of the spectrum as they go, a visual whisper of motion that reaches us without a sound. Snowflakes form in clouds through a process so delicate it seems almost like thought. A tiny particle of dust or pollen becomes the nucleus, and water vapor in the cold air begins to freeze onto it, molecule by molecule. The shape that emerges depends on temperature and humidity, and because each flake falls through slightly different conditions, each one grows into a unique structure. The classic six-pointed symmetry arises from the hexagonal arrangement of water molecules in ice, a geometry written into the nature of hydrogen bonds. As the crystal tumbles through the cloud, arms extend, branches split, and intricate patterns develop, all in silence. Millions of flakes are forming at this moment in winter clouds around the world, each one a tiny sculpture of frozen water, and not one makes a sound as it takes shape. Even when they fall, drifting down through cold air to settle on the ground, they land without noise, accumulating into drifts and blankets that muffle the world further, wrapping the landscape in layered quiet. Your bones are constantly remodeling themselves, breaking down and building up in a silent cycle that continues throughout your life. Cells called osteoclasts dissolve old bone tissue, creating tiny cavities, while other cells called osteoblasts fill those spaces with fresh bone matrix that gradually hardens with calcium and phosphate. This process happens continuously in every bone in your body, without any sensation or sound. Over the course of about 10 years, your entire skeleton is replaced, atom by atom, cell by cell. The architecture of your bones responds to the forces you place on them, growing denser where stress is frequent, thinning where it is not. Astronauts in the weightlessness of space lose bone density because their skeletons no longer bear the constant load of gravity, and the quiet remodeling shifts toward breakdown. Here on Earth, as you rest, your bones are engaged in their slow, silent work of renewal, a process as fundamental to your body as breathing, yet one you will never feel or hear. The great ocean currents move vast rivers of water across the planet in a circulation that has no voice. The Gulf Stream carries warm water from the Caribbean up along the eastern coast of North America and across the Atlantic toward Europe, transporting more water than all the rivers on Earth combined. These currents are driven by differences in temperature and salinity, by the spin of the Earth, by the wind, and by the shape of the ocean floor. They flow steadily, year after year, century after century, moving heat from the equator toward the poles and shaping the climate of entire continents. A single molecule of water might take 1,000 years to complete the full circuit of the global conveyor belt, sinking in the cold polar seas, creeping along the bottom of the ocean, rising again in distant waters, and drifting back toward the surface. All of this happens in silence, beneath the waves, unseen and unheard, a planetary engine of circulation that has been running since the oceans formed. In the soil beneath a forest, an ancient conversation unfolds through chemistry alone. Tree roots release sugars into the ground, feeding symbiotic fungi that wrap around them in delicate sheaths. In return, The fungi extend thread-like filaments called hyphae through the soil, vastly increasing the surface area available for absorbing water and nutrients. These fungal networks connect tree to tree, sometimes linking dozens or even hundreds of individuals across a forest. Through these connections, trees can share resources, sending carbon to a neighbor that stands in shade, receiving phosphorus in return. Some researchers describe this as a kind of communication, though it is not language as we know it, only the silent exchange of molecules through living conduits in the earth. The network has been called the Wood Wide Web, and it operates entirely without sound, a hidden architecture of cooperation beneath every footstep you take in the woods. Glaciers carve valleys and shape mountains, but if you stand beside one, you will hear only occasional creaks and groans, the sound of ice adjusting to its own immense weight. The actual process of erosion, the grinding of rock beneath the glacier, happens too slowly and too deeply to produce any sound you could hear. The ice moves forward perhaps a few inches a day, perhaps a few feet a year, and as it goes, it plucks stones from the bedrock and drags them along, scouring the valley floor. Over thousands of years, this silent scraping can carve a U-shaped valley from a V-shaped river gorge, can polish bedrock into smooth curves, can carry boulders hundreds of miles from their origin. The glaciers that covered much of North America and Europe during the last ice age reshaped entire landscapes in this way, and they did so in a quiet that was broken only by the wind and the occasional crack of ice calving from the terminus. The great work of sculpture happened in near silence, patient and inexorable. Photosynthesis is the most important chemical reaction on Earth, and it proceeds without a sound. Inside every green leaf, inside every blade of grass, and every microscopic algae cell in the ocean, chlorophyll molecules are capturing photons of sunlight and using that energy to split water molecules. The hydrogen is then combined with carbon dioxide from the air to build sugars, and oxygen is released as a byproduct. This process feeds nearly every living thing on the planet, either directly or indirectly, and it has been filling the atmosphere with breathable oxygen for billions of years. Right now, in daylight hours, trillions upon trillions of these reactions are taking place across the Earth's surface, in forests and fields and floating meadows of phytoplankton, and they happen in absolute silence. There is no hum of machinery, no click of switches, only the quiet absorption of light and the rearrangement of atoms, a molecular alchemy that sustains the living world. The planets orbit the sun in silence, held in their paths by gravity's invisible hand. Mercury completes its swift circuit in just 88 days, while distant Neptune takes more than 160 years to make a single trip around our star. Each planet moves through the vacuum of space, where there is no air to vibrate, no medium to carry sound. If you could somehow stand in space and watch the solar system from above, you would see the planets sweeping along their elliptical paths like dancers in a slow ballet, but you would hear nothing at all. Even the sun itself, a roiling sphere of plasma, where nuclear fusion releases the energy of millions of hydrogen bombs every second, makes no sound that can travel through the void. The entire solar system is a symphony of motion and light, but it plays in perfect silence, and it has done so for 4.5 billion years. Inside your cells, molecular machines are working at this very moment, assembling proteins from amino acids with a precision that rivals any human technology. Ribosomes, themselves made of RNA and protein, read the genetic instructions carried by messenger RNA and stitched together chains of amino acids in exactly the right order. Each ribosome can add about 20 amino acids per second, and a single cell may contain millions of ribosomes, all working simultaneously. The process is called translation, and it happens in every living cell on Earth, from bacteria to redwoods to you. These molecular machines have no moving parts in the mechanical sense, no gears or levers, only the shifting of chemical bonds and the folding of shapes. They work in silence, deep within the cellular fluid, building the proteins that form your muscles, your enzymes, your hormones, everything that makes your body function. The hum of life at this scale is not a sound but a dance of atoms, and it unfolds without a whisper. The Sahara Desert was once green, covered with lakes and grasslands where hippos and crocodiles thrived. This transformation happened not once, but many times, driven by slow shifts in Earth's orbit and tilt that changed the distribution of sunlight and the patterns of monsoon rains. The greening and drying of the Sahara follows a cycle that repeats roughly every 20,000 years, and the transition from savanna to sand dunes takes place over centuries, quietly, as rainfall diminishes and vegetation retreats. Ancient rock art in the heart of the desert shows giraffes and cattle, evidence of a time when humans and animals lived where now there is only stone and sand. The desert does not announce its changes with thunder or earthquake, only with the gradual disappearance of water, the slow death of the last trees, the silent advance of dunes that bury the past. And then, millennia later, the rains return and green things grow again, and the cycle continues in its patient, soundless rhythm. Stalactites hang from cave ceilings like stone icicles, and they grow so slowly that a single inch might represent a century or more. Water seeps through cracks in the rock above, dissolving limestone as it goes, and when it reaches the cave ceiling, a drop hangs there for a moment before falling. In that brief pause, a tiny amount of carbon dioxide escapes from the water into the cave air, and a microscopic layer of calcite precipitates out, left behind like a mineral ghost of the drop. Over thousands of drips, over thousands of years, the stalactite extends downward, ring by ring, layer by layer. If a stalagmite grows up from the floor beneath it, fed by the same dripping water, the two may eventually meet and fuse into a column. The entire process is so gradual that no human lifetime is long enough to see significant change, and it happens in the deep silence of caves where no light reaches, where the only sound is the occasional drip of water echoing in the darkness. The cosmic microwave background is the afterglow of the Big Bang, a faint radiation that fills the entire universe. It was released about 380,000 years after the beginning of everything, when the universe had cooled enough for atoms to form and light to travel freely for the first time. That ancient light has been stretched by the expansion of the universe, shifted from visible wavelengths into microwaves, and it now reaches us from every direction in the sky. If your eyes could see microwaves, the entire sky would glow with a soft, even light, a relic of the moment when the universe became transparent. This radiation is remarkably uniform, varying in temperature by only a few millionths of a degree from place to place, and it carries information about the structure of the early universe, the seeds of galaxies and clusters that would form billions of years later. It is a silent message from the dawn of time, traveling through space for more than 13 billion years to reach us, a whisper of light that speaks of beginnings. Coral reefs grow in tropical seas, built by tiny animals called polyps that secrete calcium carbonate skeletons. Each polyp is only a few millimeters across, and it lives in a symbiotic relationship with algae that provide it with food through photosynthesis. When a polyp dies, its skeleton remains, and new polyps build on top of it, layer upon layer, generation upon generation. Over centuries and millennia, this process creates massive structures, reefs that can stretch for hundreds of miles and rise from the ocean floor to just below the surface. The Great Barrier Reef, the largest living structure on Earth, has been growing for about 20 million years, though its current form is much younger, only about 8,000 years old. dating back to the end of the last ice age when sea levels rose and flooded the continental shelf. The reef grows in silence, beneath the waves, a slow accumulation of limestone built by countless small lives, each one adding its tiny contribution to a structure visible from space. Your brain generates electrical signals constantly, even when you are at rest, even when you sleep. Neurons communicate by sending pulses of electrical charge down their length and releasing chemical messengers called neurotransmitters at their tips. These signals travel at speeds ranging from a few feet per second to more than 200 miles per hour, depending on the type of neuron, and they form patterns of activity that correspond to thoughts, memories, sensations, and movements. Right now, as you read or listen to these words, millions of neurons are firing in coordinated rhythms, creating the experience of understanding, of meaning. Yet all of this happens in silence. The electrical signals are too small and too fast to produce any sound, and the chemical exchanges at synapses are molecular events that occur without vibration or noise. The most complex structure in the known universe, the human brain, does its work in a quiet that is broken only by the distant pulse of blood flowing through its vessels. The Andromeda Galaxy is moving toward us, and in about 4 billion years, it will collide with the Milky Way. This is not a violent crash in the sense of stars smashing into one another, because the distances between stars are so vast that even when two galaxies merge, individual stars almost never collide. Instead, the galaxies will pass through each other, their shapes distorted by gravity, stars flung into new orbits, and eventually the two will settle into a single, larger elliptical galaxy. The whole process will take hundreds of millions of years, and it will unfold in the silence of space, a slow gravitational dance on a scale almost too large to comprehend. If humans or their descendants are still around to witness it, they will see the night sky transform over millennia, the band of the Milky Way warping and twisting, new constellations forming as stars shift, and through it all, not a sound will reach their ears, only light, only the silent testimony of motion and change. In the deep ocean, far below the reach of sunlight, hydrothermal vents pour superheated water into the cold abyss. These vents form where tectonic plates pull apart and seawater seeps down into cracks in the Earth's crust, is heated by magma below, and then rushes back up, laden with dissolved minerals. When the hot water meets the cold ocean, those minerals precipitate out, forming chimneys of rock that can grow several feet per day, far faster than any cave formation. Around these vents, entire ecosystems thrive in the darkness, based not on photosynthesis, but on chemosynthesis, the process by which bacteria extract energy from chemicals like hydrogen sulfide. Tube worms, clams, crabs, and shrimp cluster around the vents, feeding on the bacteria or on each other, living in a world that never sees the sun. The vents themselves are loud with the rush of water and the creak of shifting rock, but the life that depends on them goes about its business in relative quiet, adapted to a realm of eternal night and crushing pressure, far removed from the surface world. The moon is slowly drifting away from Earth, receding at a rate of about 1.5 inches per year. This happens because of the tidal forces between the two bodies. The moon's gravity pulls on Earth's oceans, creating the tides, and the friction of those tides against the ocean floor and coastlines gradually slows Earth's rotation. As Earth loses rotational energy, the moon gains orbital energy and moves farther away. This process has been going on since the moon formed, more than 4 billion years ago, likely from the debris of a giant impact between the young Earth and a Mars-sized object. In the distant past, the moon was much closer, and the days were shorter, perhaps only 6 hours long. In the far future, if this process continues undisturbed, the moon will drift so far away that total solar eclipses will no longer be possible. because the moon will appear too small in the sky to cover the sun. All of this happens in silence, a gradual unwinding of gravitational energy, measured in inches per year, invisible to the eye, detectable only through precise measurement over decades. Seeds can wait in the soil for years, sometimes decades, even centuries, before they germinate. They lie dormant, their metabolism slowed to nearly nothing, protected by tough seed coats that resist water and decay. Inside, the embryonic plant is alive but paused, waiting for the right conditions, the right temperature, the right amount of moisture, sometimes even the right kind of light or the chemical signal of smoke from a fire. When those conditions arrive, the seed absorbs water, swells, and begins to grow, breaking through its coat and sending a root down into the soil and a shoot up toward the light. Some seeds have been found in ancient archaeological sites and successfully germinated after hundreds of years. The oldest seed ever sprouted was a date palm seed from Masada in Israel, more than 2,000 years old, and it grew into a healthy plant. The silence of dormancy is profound, a state of suspended life that can outlast empires, waiting patiently for the moment to awaken. The Earth's magnetic field is generated deep within the planet, in the outer core, where liquid iron flows in great convective currents driven by heat from the inner core. These currents of molten metal, moving through the planet's rotation, create electrical currents, and those electrical currents generate the magnetic field that surrounds the Earth and extends far out into space. This field protects us from the solar wind, a stream of charged particles constantly flowing from the sun, and it guides the navigation of birds, sea turtles, and other animals that can sense its direction. The field is not static. It shifts and changes over time, and occasionally it reverses, with magnetic north and south swapping places. These reversals happen irregularly, sometimes every few 100,000 years, sometimes millions of years apart, and the process takes several thousand years to complete. During a reversal, the field weakens and becomes more complex, with multiple poles appearing and disappearing. The entire system operates in silence, deep beneath our feet, a planetary dynamo that has been running for billions of years, unseen and unheard, shaping the space around us and shielding life from the harshness of the sun. Lichens grow on bare rock in places where almost nothing else can survive. On mountaintops, in deserts, in the frozen expanses of Antarctica. A lichen is not a single organism, but a partnership between a fungus and an alga, or cyanobacterium. The fungus provides structure and protection, while the photosynthetic partner provides food. Together, they can colonize surfaces that would kill either one alone, slowly breaking down the rock with acids they secrete, creating tiny pockets of soil where other plants may eventually take root. Lichens grow extraordinarily slowly, sometimes less than a millimeter per year, and some individuals are thought to be thousands of years old, among the oldest living things on Earth. They grow in silence, spreading across stone in patterns of gray and green and orange, patient and persistent, transforming barren surfaces into the beginnings of ecosystems, one microscopic layer at a time. The rings of Saturn are made of countless pieces of ice and rock, ranging in size from grains of sand to chunks as large as houses. They orbit the planet in a flat disk, held in place by gravity and shaped by the gravitational influence of Saturn's many moons. The rings are bright and beautiful, reflecting sunlight with a brilliance that makes them visible even through a small telescope. But they are also surprisingly thin, in some places only about 30 feet thick despite being hundreds of thousands of miles across. The particles in the rings collide constantly, gently, their motions governed by gravity and momentum, and these collisions happen in silence, in the vacuum of space. The rings are not permanent. They are probably only a few 100 million years old, young by astronomical standards, and they are slowly spiraling down towards Saturn, pulled by the planet's gravity and by interactions with its magnetic field. In another 100 million years, they may be gone, leaving Saturn a plain, ringless world, and the entire process will unfold without a sound. Your liver is working right now, performing more than 500 different chemical functions, filtering your blood, producing bile, storing energy, breaking down toxins, and synthesizing proteins. It processes everything you eat and drink, deciding what to keep, what to store, what to convert, and what to eliminate. The liver is one of the few organs that can regenerate itself. If part of it is damaged or removed, the remaining tissue can grow back to nearly full size. All of this happens in silence, deep within your abdomen, a tireless chemical factory that never stops, never rests, working day and night to keep your internal environment stable. You will never feel it working, never hear it, but without it, you could not survive more than a day or two. It is a quiet miracle of biology, a testament to the complexity and elegance of the systems that sustain you. The fossil record is a library written in stone, preserving the shapes of ancient life in layers of sediment that have hardened over millions of years. When an organism dies in the right conditions, buried quickly in mud or sand, its soft tissues decay, but its hard parts, bones or shells, may be replaced molecule by molecule with minerals, turning them to stone. The process is called permineralization, and it happens slowly, over thousands or millions of years, as groundwater carrying dissolved minerals seeps through the buried remains. The result is a fossil, a stone replica of something that once lived, capturing details down to the microscopic level. Fossils form in silence, deep underground, in darkness, and they wait there until erosion or excavation brings them back to the surface. Each one is a message from the past, a snapshot of life as it was in ages almost beyond imagination, and the silence in which they form is the silence of deep time, patient and absolute. Black holes are regions of space-time where gravity is so strong that not even light can escape. They form when massive stars collapse at the end of their lives, their cores compressing into a point of infinite density called a singularity, surrounded by an event horizon, the boundary beyond which nothing can return. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners. They only pull in matter that comes very close, and from a distance, their gravity is no stronger than that of the star that formed them. Around some black holes, especially those that are actively feeding on surrounding gas, there are disks of superheated matter that glow brilliantly and emit jets of particles at nearly the speed of light. But the black hole itself, the region inside the event horizon, is silent and invisible, a void in space where time and space themselves are twisted beyond recognition. If you could somehow survive near one, you would see the universe around you distorted, light bent into strange arcs, time dilated so that distant events seem to speed up, but you would hear nothing, because sound cannot travel through the vacuum, and nothing escapes from within. The silence continues in the slow expansion of tree rings, those concentric circles that form year after year within the trunk of every growing tree. Each spring, as warmth returns and water rises through the roots, a new layer of cells begins to form just beneath the bark. These cells are large and thin-walled, built for rapid growth and water transport during the abundant season. Then, as summer fades and autumn approaches, the tree shifts its strategy. The new cells become smaller, denser, thicker-walled, preparing for the hardship of winter. This transition creates a visible line, a boundary between one year and the next. And all of this happens without a whisper. The tree does not announce its growth. It simply adds layer upon layer, ring upon ring, in a patient accumulation that can continue for centuries. Some bristlecone pines have been growing this way for more than 4,000 years. Each ring a silent record of single year's weather, a single year's survival. You could place your hand on the bark and feel nothing of this quiet construction happening just beneath the surface. Beneath the surface of your skin, your body is constantly renewing itself in silence. Every minute, millions of your cells die and millions more are born to replace them. The cells lining your stomach are replaced every few days. The outermost layer of your skin is entirely new every few weeks. Red blood cells circulate for about 4 months before they are quietly broken down and recycled. Even the bones that feel so solid and permanent are continuously remodeling, with specialized cells dissolving old bone tissue while others lay down new mineral matrix. This process is called bone remodeling, and it happens throughout your entire life. It is how broken bones heal, how your skeleton adapts to the stresses you place upon it, how calcium is released into your bloodstream when needed. And it all occurs in absolute silence, a hidden conversation between cells, a constant renovation project that you will never hear, never feel, unless something goes wrong. Your body is always quietly building itself, maintaining itself, preparing itself for tomorrow. In the deep ocean, far from any coastline, there are regions where the water is so still that it has not mixed with the surface for more than 1,000 years. These are the deep basins of the abyssal plain, where cold, dense water sinks and settles, trapped by the geography of the seafloor. The water here is near freezing, just a few degrees above 0 Celsius. The pressure is immense, hundreds of times greater than at the surface, and the darkness is total. No sunlight has reached these depths in all the time this water has rested here. The currents that do exist move slowly, sometimes just a few centimeters per day, a pace so gradual that it would take years to travel the distance you might walk in an afternoon. Scientists can measure the age of this water by analyzing the decay of radioactive isotopes dissolved within it, the same method used to date ancient artifacts. And what they find is water that sank from the surface during the Middle Ages, water that has been resting in silent darkness ever since, undisturbed, patient, waiting. It is one of the slowest movements on Earth, a circulation so gentle it borders on stillness. High above the Earth, in the thermosphere where the atmosphere is so thin it barely exists, satellites orbit in near silence. At this altitude, there are so few air molecules that sound cannot travel. A collision between 2 satellites, an event that would be catastrophic and violent, would produce no sound at all. The metal would crumple, fragments would scatter in all directions, solar panels would shatter into glittering shards, but all of it would happen in complete silence. The astronauts aboard the International Space Station, orbiting within this same thin atmosphere, experience a similar quiet. Outside their modules, there is no wind, no rustle, no hum of air. Inside, they hear the fans, the pumps, the equipment that keeps them alive. But when they perform a spacewalk and float in the vacuum beyond, they're surrounded by a silence that is both profound and unsettling. They can hear their own breathing inside the helmet, the crackle of the radio, but nothing from the universe around them. It is a silence that reminds them how far they are from the world of sound, how deeply they have ventured into a realm where noise has no meaning. The formation of a snowflake is a silent act of geometry. It begins with a single speck of dust or pollen drifting through a cold cloud. Water vapor in the air condenses onto this tiny nucleus, freezing into ice. As more vapor molecules arrive, they attach to the growing crystal in patterns determined by the molecular structure of ice itself. Water molecules naturally bond at angles of approximately 120 degrees, and this gives every snowflake its 6-sided symmetry. But the exact shape of each snowflake depends on the temperature and humidity it encounters as it falls. A slight change in conditions will alter the way the crystal grows, creating branches, needles, plates, or columns. Because each snowflake follows a slightly different path through the atmosphere, encountering slightly different conditions, each one develops a unique structure. And all of this happens in silence. The water molecules do not click into place. The crystal does not chime as it grows. It simply forms, delicate and intricate, falling gently toward the ground, one of billions, each one different, each one silent. In the soil beneath a forest, earthworms move through the darkness, quietly transforming the earth. They consume organic matter, fallen leaves, decaying roots, dead insects, and pass it through their digestive systems, breaking it down into simpler compounds. What emerges from the other end is castings, a nutrient-rich material that is far more fertile than the soil they consumed. These castings improve soil structure, increase water retention, and provide essential nutrients for plant roots. A single earthworm may consume and process its own weight in soil every day. In a healthy forest, there may be hundreds of earthworms in every square meter, each one quietly eating, digesting, and enriching the soil. Over the course of a year, they can move tons of earth, aerating it, mixing it, turning the forest floor into a living, breathing medium for growth. Charles Darwin spent years studying earthworms and concluded that few creatures have played a more important role in the history of the world. And they do all of this in silence, without fanfare, without recognition, simply moving through the dark earth, one small body at a time. The light from the Andromeda Galaxy, our nearest large galactic neighbor, has been traveling through space for 2.5 million years before it reaches your eyes. When that light began its journey, early humans were just beginning to walk upright on the plains of Africa. The light has crossed the vast emptiness between galaxies, moving at 300,000 kilometers per second, never slowing, never stopping, never making a sound. It has passed through clouds of gas and dust, through regions where stars are being born and regions where stars have died. It has traveled through the expanding fabric of space itself, stretched slightly by the universe's growth. And now, on a clear night, if you look up at the sky and find the faint smudge of light that is Andromeda, you are seeing that ancient light, photons that have been traveling in silence for longer than our species has existed. It is a connection across time and space, a silent message from a distant island of stars, reaching you in the quiet of the night. Deep within the Earth's mantle, convection currents move in slow, silent cycles that drive the motion of tectonic plates. The mantle is not liquid, but it is not entirely solid either. It behaves like a very thick, viscous fluid, capable of flowing over geological timescales. Heat from the Earth's core warms the lower mantle, causing it to expand and become less dense. This warmer material slowly rises, taking millions of years to ascend. As it nears the surface, it cools, becomes denser, and eventually sinks back down. This creates an pattern, a convection cell that transfers heat from the deep interior toward the surface. The movement is incredibly slow, perhaps a few centimeters per year, but it is relentless. It is this silent circulation that pulls continents apart, pushes mountains upward, and recycles the ocean floor. It is the engine that powers plate tectonics, the force that has shaped the surface of our planet for billions of years. And it happens in the silent depths, far below the reach of human observation, a slow churning that will continue long after we are gone. In the autumn, deciduous trees perform a quiet act of preparation. As the days grow shorter and temperatures drop, the trees begin to withdraw resources from their leaves. Chlorophyll, the green pigment that captures sunlight for photosynthesis, breaks down and is reabsorbed into the branches and trunk. Without the chlorophyll, other pigments that were always present in the leaf become visible. Carotenoids that produce yellow and orange hues, anthocyanins that create reds and purples. This is why leaves change color in the fall. But the tree is not simply putting on a show. It is salvaging valuable nutrients before the leaves are discarded. At the base of each leaf stem, a special layer of cells called the abscission layer begins to form. These cells create a barrier that eventually seals off the leaf from the rest of the tree. When the connection is severed, the leaf falls. The tree is quietly prepared for winter, storing what it needs and letting go of what it cannot maintain. And all of this happens without sound, a gentle transition from growth to dormancy, from green to gold, from abundance to rest. The cosmic microwave background radiation that fills the universe is not just ancient light. It is also remarkably uniform. When scientists map this radiation across the entire sky, they find that it is almost exactly the same temperature in every direction, 2.725 Kelvin, just a few degrees above absolute zero. But there are tiny variations, fluctuations of only a few millionths of a degree. These minute differences are incredibly important. They represent the seeds of all structure in the universe. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter, which increased the gravity further. Over hundreds of millions of years, these tiny ripples grew into the galaxies, galaxy clusters, and vast cosmic webs we see today. Everything, every star, every planet, every atom in your body can trace its origin back to these silent, nearly imperceptible fluctuations in the early universe. They are the whispers of creation, frozen into the oldest light we can see, a quiet blueprint for everything that would come after. In a human eye, a remarkable molecule called rhodopsin waits in the darkness, ready to detect even a single photon of light. Rhodopsin is found in the rod cells of your retina, the cells responsible for vision in dim conditions. Each rhodopsin molecule consists of a protein called opsin bound to a light-sensitive molecule called retinal. When a photon strikes retinal, it causes the molecule to change shape in a fraction of a second. This shape change triggers a cascade of chemical reactions within the rod cell, amplifying the signal until it is strong enough to send an electrical impulse to your brain. This process is so sensitive that, under ideal conditions, your eye can detect just a few photons, the smallest possible units of light. And it all happens in silence. The photon does not announce its arrival. The molecule does not click as it changes shape. The signal simply flows quietly and efficiently from light to chemistry to electricity to perception. It is one of the most sensitive detection systems in nature, and it operates without a sound. Glaciers in the polar regions calve icebergs into the sea in events that seem sudden and dramatic. But the process that leads to calving is slow and silent. The glacier flows toward the ocean over many years, pushed by the weight of ice accumulating behind it. As the front edge extends over the water, it becomes unsupported, a cantilever of ice hanging over the sea. Cracks form, propagating slowly through the ice, weakened by the stress and by the warmth of the water below. Eventually, the ice can no longer support its own weight, and a section breaks away, falling into the ocean. The splash and the rumble can be heard for miles, but all the years of flow, all the slow spreading of cracks, all the patient advance of the glacier, these happen in near silence. The iceberg that results will drift with the currents, melting slowly as it moves into warmer waters, a frozen remnant of ancient snow, traveling quietly toward its dissolution. Inside a chrysalis, a caterpillar undergoes one of the most profound transformations in nature, and it does so in complete silence. After the caterpillar has eaten enough and grown as large as it will, it finds a safe place and forms a protective casing around itself. Inside this chrysalis, the caterpillar's body begins to break down. Special cells called imaginal discs, which have been dormant throughout the caterpillar's life, now activate. These cells use the dissolved tissue of the caterpillar as raw material to build entirely new structures. wings, legs, antennae, compound eyes, and all the other parts of an adult butterfly. The process takes days or weeks, depending on the species. The transformation is so complete that if you were to open a chrysalis midway through, you would find a soupy mixture of cells, barely recognizable as a living creature. Yet from this quiet chaos, order emerges. The butterfly forms, piece by piece, in the darkness and silence of the chrysalis, until finally it is ready to emerge, wings still soft and crumpled, into the light of day. The sand dunes of the world's deserts migrate slowly across the landscape, moved by the wind in a process that is both simple and elegant. Wind blowing over a dune carries sand grains up the gentle windward slope. When the grains reach the crest, they tumble down the steep leeward side, coming to rest at the angle of repose, the steepest angle at which the sand remains stable. Grain by grain, the dune moves forward, advancing in the direction of the prevailing wind. The rate of movement depends on the size of the dune and the strength of the wind. Small dunes may move several meters in a year. Large dunes, like the towering star dunes of the Sahara, may take centuries to move the same distance. But the process is continuous. The desert is never truly still. It is always shifting, always rearranging itself, one grain at a time, in silence. Ancient caravan routes have been buried, archaeological sites have been covered and then revealed again, and the dunes move on, indifferent, patient, shaped by forces that have no memory and no intention. In the vacuum of space, the solar wind streams outward from the sun, a flow of charged particles, mostly protons and electrons, moving at hundreds of kilometers per second. This wind is invisible and silent, detectable only by its effects. When it reaches Earth, it encounters our planet's magnetic field, which deflects most of the particles around us, protecting the surface from radiation. But some particles are funneled along the magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere. These collisions excite the atoms, causing them to emit light, creating the auroras, the northern and southern lights. From the ground, the auroras appear as shimmering curtains of green, red, and purple light, dancing across the sky. They are beautiful and mesmerizing, but they are also silent. The collisions that create the light happen at altitudes where the atmosphere is too thin to carry sound. The solar wind itself, the journey of particles across 93 million miles of space, produces no sound. It is a silent storm, a river of energy flowing invisibly through the solar system, revealed only by the glow it creates when it touches our world. The process of fossilization is one of the slowest transformations in nature, and it happens in silence over millions of years. When an organism dies, its soft tissues usually decay quickly, consumed by bacteria and scavengers. But if the body is buried rapidly, by sediment in a river, by mud in a swamp, by ash from a volcano, the decay can be slowed. Over time, more sediment accumulates on top, and the pressure increases. Minerals dissolved in groundwater begin to seep into the bones or shell or wood, filling the tiny spaces within the tissue. Slowly, the original material is replaced, molecule by molecule, with stone. The shape remains, but the substance changes. What was once living tissue becomes rock, a replica in mineral form. This process can take millions of years. The fossil that results is a silent witness to a vanished world, a record of life preserved not by intention, but by chance, by the quiet chemistry of water and stone and time. In the center of our galaxy, there is a supermassive black hole called Sagittarius A star. It contains the mass of more than 4 million suns, compressed into a region smaller than the orbit of Mercury. Despite its immense gravity, Sagittarius A* is relatively quiet. It is not currently consuming large amounts of matter, so it does not shine brightly like some other supermassive black holes. Instead, it sits in the darkness, a silent gravitational anchor around which hundreds of billions of stars orbit. Occasionally, a star or a cloud of gas wanders too close, and the black hole's gravity tears it apart, heating the material to millions of degrees and causing it to emit X-rays. But most of the time, Sagittarius A* is quiescent, a dark heart at the center of the Milky Way, invisible except for the effect it has on the stars that orbit it. Astronomers have tracked these stars for decades, watching them swing around an invisible point, their orbits revealing the presence of something massive and dark, something that pulls but does not shine, something that exists in silence. Your brain consumes about 20% of your body's energy, even though it makes up only about 2% of your body weight. Most of this energy is used not for conscious thought, but for maintaining the basic activity of neurons, the cells that transmit electrical signals. Even when you're resting, even when you're asleep, your neurons are firing, communicating with each other, maintaining the networks that make thought and memory possible. This activity is called the brain's default mode, and it is essential for processing information, consolidating memories, and preparing for future tasks. And it all happens in silence. You cannot hear your neurons firing. You cannot feel the electrical impulses racing along nerve fibers. The brain's work is invisible and inaudible, a constant hum of activity that underlies every moment of your conscious experience. It is the quiet machinery of thought, the silent foundation of everything you perceive and feel and remember. In the deep ocean, hydrothermal vents release superheated water from cracks in the seafloor, creating oases of life in the darkness. The water, heated by contact with magma below, can reach temperatures of 400 degrees Celsius, but does not boil because of the immense pressure at these depths. As the hot water mixes with the cold ocean water, minerals dissolved in the vent fluid precipitate out, forming towering chimneys of rock. These chimneys can grow several meters tall, and they release plumes of dark, mineral-rich water that look like smoke, giving them the name black smokers. Around these vents, unique ecosystems thrive, based not on sunlight, but on chemosynthesis. Bacteria use the chemicals in the vent water, hydrogen sulfide, methane, as an energy source, forming the base of a food web that includes giant tube worms, eyeless shrimp, and pale crabs. The vents themselves are silent, the water flowing without sound in the deep, the minerals precipitating quietly, the bacteria working without fanfare. It is a hidden world, a reminder that life can flourish in the most unlikely places, powered by the silent heat of the Earth's interior. The moon's surface is covered with a fine dust called regolith, the product of billions of years of meteorite impacts. Each impact, large or small, shatters rock and grinds it into smaller and smaller particles. Because the moon has no atmosphere, there is no wind or water to smooth or sort this dust. It remains sharp and jagged, clinging to everything it touches. When the Apollo astronauts walked on the moon, they found that the regolith stuck to their spacesuits, their equipment, their boots. It was difficult to brush off, and it had a distinctive smell, described by some as like gunpowder or spent fireworks. Though, of course, on the moon itself, there is no air to carry scent or sound. The dust is also electrostatically charged by the solar wind, which causes it to levitate slightly above the surface, creating a faint, ghostly glow at the lunar horizon during sunrise and sunset. This phenomenon, called the lunar horizon glow, was observed by astronauts and is still not fully understood. It is a silent, subtle effect, a reminder that even in the stillness of the moon, there are forces at work, shaping and moving the surface in ways we are only beginning to comprehend. In the coldest regions of space, in the molecular clouds where stars are born, temperatures drop to just a few degrees above absolute zero. At these temperatures, atoms move very slowly, and molecules can form that would be unstable in warmer environments. Astronomers have detected more than 200 different molecules in these clouds, including water, ammonia, formaldehyde, and even complex organic compounds like amino acids and sugars. These molecules form on the surfaces of tiny dust grains, where atoms can meet and bond in the cold and dark. The process is slow and silent, a gradual accumulation of complexity in the most inhospitable environment imaginable. Some scientists believe that these molecular clouds may have seeded the early Earth with the building blocks of life, delivering organic compounds through comets and meteorites. If this is true, then the chemistry of life began not on Earth, but in the silent cold of interstellar space, in clouds of gas and dust drifting between the stars, where molecules formed and waited, frozen and patient, for a world where they could grow and change and eventually become alive. The human liver is one of the most quietly industrious organs in your body. It performs more than 500 different functions, most of which you will never notice unless something goes wrong. It filters toxins from your blood, breaking down alcohol, drugs, and metabolic waste products into safer compounds that can be excreted. It produces bile, which helps digest fats. It stores glucose in the form of glycogen, releasing it when your blood sugar drops. It synthesizes proteins essential for blood clotting. It regulates cholesterol levels. It processes nutrients absorbed from the intestines, converting them into forms your body can use. And it does all of this continuously, silently, without rest. The liver is also one of the few organs capable of regenerating itself. If part of it is damaged or removed, the remaining tissue can grow back, restoring the liver to its full size and function. This regeneration happens quietly, over weeks and months, cells dividing and differentiating, rebuilding what was lost. It is a remarkable ability, a quiet resilience built into the architecture of your body. In the rings of Saturn, billions of particles of ice and rock orbit the planet in a vast, flat disk. The particles range in size from tiny grains to house-sized boulders, and they are spread out over hundreds of thousands of kilometers. Despite their immense scale, the rings are surprisingly thin, in some places only a few meters thick. The particles are kept in place by Saturn's gravity and by the gravitational influence of its many moons, which shepherd the particles and create gaps and waves in the rings. Collisions between particles are frequent but gentle, and they help to dissipate energy, keeping the rings flat and stable. The rings are also remarkably bright, reflecting sunlight with an intensity that makes them visible even through small telescopes from Earth. But they are silent. There is no air to carry sound, no medium for vibrations to travel. The particles orbit in silence, colliding and bouncing and drifting, a vast, slow dance governed by gravity and momentum, beautiful and serene, a structure that has existed for millions of years and will continue for millions more, until eventually, slowly, the rings spiral inward and fall into the planet, their particles scattered and absorbed, their beauty fading into memory. In the soil, seeds can remain dormant for years, even decades, waiting for the right conditions to germinate. This dormancy is not simply inactivity. It is a state of suspended animation, maintained by chemical inhibitors within the seed that prevent growth. The seed is alive, its cells respiring at a very low rate, its enzymes ready but inactive. It is waiting for a signal, the right amount of moisture, the right temperature, sometimes even the right kind of light. When these conditions are met, the seed absorbs water, swelling and breaking through the seed coat. Enzymes activate, breaking down stored nutrients and converting them into energy. The embryo within the seed begins to grow, sending a root downward into the soil and a shoot upward toward the light. This process, called germination, can happen in a matter of days, but it is the culmination of a long, silent wait. Some seeds have germinated after more than 1,000 years of dormancy, brought back to life by archaeologists or by changes in their environment. They are patient beyond measure, silent witnesses to the passage of time, waiting for their moment to grow. The Earth's magnetic field extends far into space, forming a protective bubble called the magnetosphere. This field is generated by the motion of molten iron in the Earth's outer core, a process called the geodynamo. The iron is kept liquid by the intense heat of the core, and it circulates in complex patterns driven by the Earth's rotation and by convection currents. As the iron moves, it generates electrical currents, and these currents create the magnetic field. The field is not static. It fluctuates over time, and it has even reversed many times in Earth's history, with the north and south magnetic poles switching places. These reversals happen over thousands of years, and they leave a record in rocks that contain magnetic minerals. When lava cools and solidifies, the magnetic minerals align with the Earth's field at that moment, preserving a snapshot of the field's direction. By studying these rocks, scientists can reconstruct the history of the magnetic field, a silent record written in stone, a chronicle of the invisible forces that have shaped and protected our planet for billions of years. In the forests of the Pacific Northwest, nurse logs lie on the forest floor, slowly decaying and providing a foundation for new life. When a large tree falls, it creates a gap in the canopy, allowing light to reach the forest floor. The fallen tree, now a nurse log, becomes a raised platform where seeds can germinate, safe from flooding and from some ground-dwelling herbivores. As the log decays, it releases nutrients that feed the young seedlings. Fungi and bacteria break down the wood, and their activity warms the log slightly, creating a favorable microenvironment. Over decades, the log is gradually consumed, its substance transformed into soil and into the bodies of the trees growing from it. Eventually, the log disappears entirely, leaving only a line of trees, their roots arching over the space where the nurse log once lay. It is a slow, silent cycle of death and rebirth, a transfer of matter and energy from one generation to the next, a reminder that in nature, nothing is wasted, and every ending is also a beginning. The light from a candle flame is produced by a process called incandescence, the emission of light from a heated object. In the flame, tiny particles of carbon, soot, are heated to temperatures of around 1,000 degrees Celsius. At this temperature, they glow, emitting light across a range of wavelengths, which is why candlelight appears warm and yellow. The carbon particles are produced when the wax vaporizes and breaks down in the heat of the flame. Most of these particles are consumed by the flame, combining with oxygen to produce carbon dioxide and water vapor. But some escape, rising with the hot air, and these are what create the smoke if the flame is disturbed. The flame itself is a delicate balance, a region where fuel and oxygen meet and react, releasing energy as heat and light. And it burns in silence, or near silence. The faint hiss you might hear is the sound of air currents and the vaporization of wax, not the combustion itself. The flame is a quiet, steady source of light, a chemical reaction that has provided warmth and illumination for thousands of years, a small, glowing reminder of the power contained in simple molecules, waiting to be released. In the human body, the process of healing begins immediately after an injury, guided by a complex and silent choreography of cells and molecules. When you cut your skin, blood vessels are damaged, and blood begins to flow out. Within seconds, platelets in the blood are activated, clumping together to form a temporary plug. At the same time, a cascade of chemical reactions called the clotting cascade is triggered, resulting in the formation of fibrin, a protein that weaves a mesh over the wound, stabilizing the clot. White blood cells arrive to fight infection, consuming bacteria and debris. Within hours, new cells begin to migrate into the wound, laying down a framework of collagen, the protein that gives skin its strength. Blood vessels grow into the new tissue, bringing oxygen and nutrients. Over days and weeks, the wound contracts, pulling the edges together, and new skin forms over the surface. Eventually, the scar tissue is remodeled, becoming stronger and more organized, though it will never be quite as strong as the original skin. All of this happens without conscious effort, without sound, a quiet miracle of repair and regeneration that your body performs thousands of times over the course of your life. And quietly, beneath the surface of every quiet lake, there exists a world of thermal stratification that unfolds without a single sound reaching the air above. During warmer months, lakes organize themselves into distinct layers based on temperature and density, with warmer water floating atop cooler depths. This separation happens gradually, molecule by molecule, as water finds its proper place according to the physics of density. The boundary between layers, called the thermocline, can be remarkably sharp, sometimes changing several degrees within just a meter of depth. Fish and other creatures sense these invisible boundaries and often gather near them, where nutrients and oxygen mix in favorable proportions. Twice each year, in spring and autumn, when surface and deep waters reach similar temperatures, the entire lake can turn over, mixing from top to bottom in a silent circulation that renews the depths. This turnover brings oxygen downward and nutrients upward, refreshing the entire ecosystem without fanfare. The whole process is driven by nothing more than sunlight, gravity, and the peculiar property of water that makes it densest at 4 degrees Celsius, not at its freezing point. These thermal rhythms have pulsed through lakes for millions of years, invisible architectures of temperature that shape aquatic life in silence. And in the realm of human creation, the curing of concrete happens as a quiet chemical transformation that can continue for decades after the material is poured. When water mixes with cement, a process called hydration begins, in which calcium silicate minerals react to form new crystalline structures that bind sand and gravel into solid stone. This reaction generates heat, but no sound, as trillions of microscopic crystals grow and interlock within the mixture. Most of the strength develops within the first month, but the process continues much more slowly for years, with the concrete actually becoming harder and more durable as time passes. Ancient Roman concrete, made with volcanic ash and seawater, has been curing and strengthening for over 2,000 years, and some structures are now harder than when they were first built. The silence of this process belies its importance to modern civilization, which rests upon billions of tons of concrete quietly gaining strength beneath our cities, bridges, and dams. Inside each structure, invisible chemical bonds form and reform, creating a stone that never truly finishes becoming itself. The patience of concrete reminds us that some of the strongest transformations require nothing but time and the steady, silent rearrangement of matter at the molecular scale. And far out in the solar system, beyond the orbit of Neptune, countless small worlds drift through a region called the Kuiper Belt, moving in darkness and cold that would be unimaginable to us. These objects, remnants from the solar system's formation, orbit the sun in complete silence, taking hundreds of years to complete a single revolution. They are made of rock and ice, preserved in deep freeze for more than 4 billion years, carrying within them the original chemistry of the planetary disk for which Earth and all the other worlds formed. Some are round, shaped by their own gravity, while others are irregular chunks tumbling slowly through space. Occasionally, gravitational nudges send one of these frozen wanderers inward toward the sun, where it becomes a comet, growing a tail of vapor and dust as sunlight warms its ancient ice. But most remain in the outer darkness, silent witnesses to the slow evolution of the solar system. The Kuiper belt stretches so far from the sun that sunlight there is faint and cold, barely warmer than the background glow of distant stars. These worlds see the sun as just a bright point of light, not the blazing disk we know from Earth. Their surfaces are marked by craters from impacts that happened billions of years ago, preserved perfectly in the airless cold. In this distant realm, time moves differently, measured not in days or years, but in epochs of orbital mechanics, where silence is absolute and change comes only through the patient mathematics of gravity. And within the cells of your own body, proteins fold into their functional shapes through a process that happens thousands of times per second, yet never makes a sound. When a protein is first synthesized as a chain of amino acids, it exists as a flexible string with no particular structure. But almost immediately, the chemical properties of the amino acids cause the chain to fold upon itself, guided by attractions and repulsions between different parts of the molecule. Within milliseconds, the protein finds its correct three-dimensional shape, the one configuration among countless possibilities that allows it to perform its specific function. This shape might be a pocket that binds to a particular molecule, or a channel that allows certain ions to pass through a membrane, or a scaffold that provides structural support. The folding happens spontaneously, driven by the fundamental physics of molecular interactions, with no instruction manual and no external guidance. Sometimes proteins misfold, and when they do, the cell has quality control systems that recognize the error and either refold the protein correctly or break it down for recycling. The entire process is so reliable that your body folds trillions upon trillions of proteins correctly every single day, each one finding its proper shape in silence. Understanding protein folding is one of the great challenges of modern biology, because the shape of a protein determines its function, and knowing how amino acid sequences translate into three-dimensional structures would unlock countless secrets of health and disease. Yet despite decades of research, the full complexity of how a simple chain becomes a working molecular machine remains partly mysterious, a quiet miracle happening continuously in every living cell. And across the surface of the Earth, the slow creep of soil downslope reshapes landscapes through a process called soil creep, which moves Earth downhill so gradually that it can only be detected over years or decades. Gravity constantly pulls on every particle of soil, and while friction and plant roots hold most of it in place, tiny movements accumulate over time. Freeze-thaw cycles lift soil particles slightly when ice forms beneath them, and when the ice melts, the particles settle a tiny bit downhill from where they started. The expansion and contraction of soil as it wets and dries has a similar effect. Burrowing animals move soil as they dig, and the material they displace tends to shift slightly downslope. Tree roots grow and die, creating spaces that fill with soil from uphill. All these small movements, none of them dramatic, none of them noisy, add up to a slow but persistent flow of earth down every slope. Over centuries, this silent creep can move soil meters downhill, gradually smoothing sharp features and filling in hollows. Fence posts on hillsides slowly tilt downhill, and stone walls built perpendicular to slopes gradually bow downslope in the middle as the earth flows around and beneath them. This process has been reshaping landscapes for as long as there has been soil and gravity, a quiet background current in the geology of every hill and mountain. It reminds us that even solid ground is not truly solid over long enough timescales, but flows like a very, very slow liquid, responding to gravity's patient pull. And in the chemistry of the atmosphere, ozone molecules form and break apart in the stratosphere through a silent cycle that protects all life below from harmful ultraviolet radiation. Ozone, made of 3 oxygen atoms bonded together, is created when ultraviolet light from the sun strikes ordinary oxygen molecules, splitting them into individual oxygen atoms that then combine with other oxygen molecules to form ozone. This same ultraviolet light can also break ozone apart, and the molecule that absorbs the UV is destroyed in the process, but in doing so it prevents that radiation from reaching the surface. The cycle of creation and destruction reaches a natural balance, maintaining a layer of ozone in the stratosphere that acts as Earth's sunscreen. This layer is thin, fragile, and invisible, yet without it, life on land would be nearly impossible, as the UV radiation would damage DNA and make the surface a hostile place for most organisms. The ozone layer has existed for hundreds of millions of years, ever since oxygen-producing photosynthesis filled the atmosphere with enough oxygen to create this protective shield. In the late 20th century, human-made chemicals called chlorofluorocarbons began destroying ozone faster than it could be replaced, creating a thinning over Antarctica that became known as the ozone hole. International cooperation led to the banning of these chemicals, and slowly, silently, the ozone layer is recovering, a rare example of humanity recognizing and reversing environmental damage. The molecules that protect us do their work without sound or fanfare, absorbing invisible light and transforming it into harmless heat, a quiet guardian in the sky. And deep within the Earth, at the boundary between the outer core and the lower mantle, a region called the D double prime layer exhibits strange properties that scientists are only beginning to understand. This layer, about 200 kilometers thick, sits nearly 3,000 kilometers below the surface, where pressures are immense and temperatures rival the surface of the sun. The rock here behaves in ways unlike anywhere else on the planet, possibly containing dense piles of material that have accumulated over billions of years, remnants of ancient tectonic plates that sank all the way to the bottom of the mantle. These dense regions may influence the flow of the liquid iron in the outer core below, affecting the generation of Earth's magnetic field. Some scientists think the D double prime layer may also be the source of deep mantle plumes, columns of hot rock that rise slowly through the mantle to create volcanic hotspots like Hawaii and Iceland. Studying this layer is extraordinarily difficult because it can only be probed indirectly through the analysis of seismic waves from earthquakes that pass through it. These waves reveal that the layer is heterogeneous, with some regions denser than others, and that it may contain partial melts or unusual mineral phases that exist nowhere else. The D double prime layer is a frontier of Earth science, a hidden landscape at the bottom of the mantle where geology becomes strange and unfamiliar. It has existed in silence since the planet formed, shaping the dynamics of the deep Earth in ways we are only beginning to glimpse. And in the life of every tree, the transport of water from roots to leaves happens through a process called transpiration, driven by evaporation and the cohesive properties of water molecules. Water evaporates from tiny pores called stomata on the surface of leaves, and as each molecule of water exits, it pulls on the column of water behind it, creating a tension that extends all the way down through the stem to the roots. Water molecules are attracted to each other through hydrogen bonding, and this cohesion is strong enough that the entire column of water can be pulled upward without breaking, even in the tallest trees. The process requires no pump, no energy input from the tree beyond the opening and closing of stomata, and no sound accompanies the flow. Water moves through specialized cells called xylem, which are dead at maturity, forming hollow tubes that run from root to leaf. The tallest trees can lift water more than 100 meters against gravity, purely through the physics of evaporation and cohesion. On a warm, sunny day, a large tree can transpire hundreds of liters of water, pulling it from the soil and releasing it into the atmosphere. This silent flow is essential not only to the tree but to the water cycle of entire ecosystems, as forests return vast amounts of water to the air, influencing weather and climate. The mechanism is so efficient and elegant that it has operated unchanged for hundreds of millions of years, since the first vascular plants evolved the ability to transport water to aerial structures. Inside every tree, water rises in silence, defying gravity through nothing more than molecular attraction and the gentle pull of evaporation. And in the frozen continent of Antarctica, buried beneath kilometers of ice, there exist lakes of liquid water that have been sealed off from the surface for millions of years. These subglacial lakes persist because the immense pressure of the ice above lowers the freezing point of water, and because heat from the Earth's interior keeps the bottom of the ice sheet slightly warm. The largest of these, Lake Vostok, is about the size of Lake Ontario, lying beneath nearly 4 kilometers of ice. It has been isolated from the atmosphere and from sunlight for at least 15 million years, creating a unique environment that may harbor microbial life adapted to extreme cold, darkness, and isolation. Scientists have drilled through the ice to study these lakes, taking extraordinary precautions to avoid contaminating them with surface microbes. The water in subglacial lakes is ancient, and the conditions within them are thought to resemble those that might exist beneath the ice shells of moons like Europa and Enceladus, making them natural laboratories for astrobiology. The lakes are connected by rivers that flow beneath the ice, moving slowly in response to the pressure and topography of the bedrock below. This hidden hydrological system influences the movement of the ice sheet above, lubricating its base and affecting how glaciers flow toward the sea. The existence of these lakes was suspected for decades based on radar and seismic data, but only recently confirmed through direct sampling. They represent one of Earth's last unexplored frontiers, silent worlds of cold darkness that have existed beneath the ice for longer than our species has walked the planet. And within the structure of crystals, atoms arrange themselves in repeating patterns that extend in 3 dimensions, creating the regular shapes and flat faces we see in minerals and gems. This atomic order arises spontaneously as a liquid or gas cools and solidifies, with each atom finding its place in the growing lattice according to the balance of attractive and repulsive forces. The process is entirely silent, yet it creates structures of remarkable beauty and precision. The angles between the faces of a crystal are determined by the geometry of its atomic lattice, and these angles are constant for a given mineral, a fact that helped early scientists deduce the existence of atoms long before they could be observed directly. Quartz crystals, for example, always form 6-sided prisms with pyramidal ends, because of the way silicon and oxygen atoms link together in spiraling chains. Salt crystals form perfect cubes because sodium and chlorine ions pack together in a simple cubic lattice. The symmetry and regularity of crystals reflect the underlying symmetry of atomic arrangements, making them visible expressions of molecular order. Some crystals grow slowly over thousands of years in caves or deep within the earth, while others form rapidly as lava cools or as water evaporates from a mineral-rich solution. The largest natural crystals ever found are selenite beams in the Cave of Crystals in Mexico, some more than 10 meters long, grown over 500,000 years in a chamber filled with hot, mineral-saturated water. These giants formed in silence, atom by atom, in a process as patient as it is beautiful. The order within crystals is a reminder that even at the atomic scale, matter seeks patterns and symmetry, creating structures that are both scientifically fascinating and aesthetically profound. And across the vast stretches of interstellar space, clouds of gas and dust collapse under their own gravity to form new stars, a process that unfolds over millions of years in absolute silence. These molecular clouds, often called stellar nurseries, are the coldest and densest regions of the galaxy, where temperatures hover just a few degrees above absolute zero. Within them, slight variations in density create regions where gravity begins to dominate over the outward pressure of gas, and these regions slowly contract, pulling in more material as they shrink. As the cloud collapses, it begins to spin faster, conserving angular momentum, and flattens into a disk with a growing protostar at the center. The protostar is not yet a true star, not yet hot enough at its core to fuse hydrogen into helium, but it glows with the heat generated by gravitational compression. Over time, as more mass accumulates and the core temperature rises, nuclear fusion ignites, and a new star is born. The disk of material around a young star may give birth to planets, as dust grains stick together to form larger and larger bodies through accretion. This entire process, from the first stirrings of collapse to the ignition of fusion, happens without sound, in the vacuum of space where there is no air to carry vibrations. We see the results in telescopes as glowing regions of star formation, like the Orion Nebula, where hundreds of young stars illuminate the cloud from which they formed. Each star is a furnace that will burn for millions or billions of years, and each began in silence, condensing from the thin material between the stars. And in the biology of sleep, your brain quietly shifts through different stages, each with distinct patterns of electrical activity that serve different functions in rest and restoration. As you drift from wakefulness into light sleep, your brain waves slow from the rapid beta waves of alertness to the gentler alpha and theta waves. Your muscles relax, your heart rate decreases, and your body begins the process of repair and consolidation. As sleep deepens, you enter slow-wave sleep, characterized by large, slow delta waves that sweep across the brain in synchronized rhythms. This is the most restorative stage, when growth hormone is released, tissues are repaired, and the immune system is strengthened. Later in the night, you enter REM sleep, where your brain becomes nearly as active as when you are awake, but your body is paralyzed to prevent you from acting out your dreams. REM sleep is when most vivid dreaming occurs, and it plays a crucial role in memory consolidation and emotional processing. Throughout the night, you cycle through these stages multiple times, each cycle lasting about 90 minutes. The transitions between stages are seamless and silent, orchestrated by complex interactions between different brain regions and neurochemical systems. Sleep is not a passive state, but an active process, essential for learning, memory, health, and well-being. The brain uses this time to clear away metabolic waste products that accumulate during waking hours, flushing them out through a system called the glymphatic system, which is most active during sleep. All of this happens without your awareness, a nightly journey through different states of consciousness, each serving its purpose in the quiet maintenance of your mind and body. And in the geology of river deltas, sediment carried by flowing water gradually builds new land where rivers meet the sea, a process that has created some of the most fertile and densely populated regions on Earth. As a river slows upon entering a larger body of water, it loses the energy needed to carry its load of silt, sand, and clay, and these particles settle to the bottom, accumulating over time. The river branches into multiple channels called distributaries, which spread the sediment across a wide area, forming the characteristic fan or triangular shape of a delta. The process is slow and silent, with each flood adding a thin layer of new sediment to the delta plain. Over centuries and millennia, this accumulation can extend the coastline kilometers out to sea, creating new land where there was once only water. The Nile Delta, the Mississippi Delta, and the Ganges-Brahmaputra Delta are all products of this patient deposition, built grain by grain over thousands of years. Deltas are dynamic environments, constantly reshaped by the river's flow, by tides, and by the settling and compaction of sediment. They are also incredibly productive ecosystems, as the sediment brings nutrients that support lush vegetation and abundant wildlife. Human civilizations have flourished on deltas for millennia, drawn by the fertile soil and easy access to water. Yet deltas are also vulnerable to changes in sea level, sediment supply, and human activities like dam construction, which can reduce the flow of sediment and cause deltas to shrink rather than grow. The silent building of deltas is one of the fundamental processes by which rivers shape coastlines and create the landscapes we inhabit. And in the realm of particle physics, subatomic particles constantly pop into and out of existence in what is called the quantum vacuum, a process that fills even empty space with fleeting energy and matter. According to quantum mechanics, the vacuum is not truly empty but seethes with virtual particles, pairs of matter and antimatter that spontaneously appear and then annihilate each other in fractions of a second. These particles exist for such brief moments that they do not violate the conservation of energy, borrowing energy from the vacuum and paying it back before the universe notices, in accordance with Heisenberg's uncertainty principle. This phenomenon has real, measurable effects, such as the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force, because fewer virtual particles can exist in the narrow gap between them than in the open space outside. The quantum vacuum also affects the behavior of atoms and the properties of fundamental forces. It is a reminder that at the smallest scales, reality is far stranger than our everyday experience suggests, filled with constant activity and fluctuation even in the absence of any real particles. This silent quantum fizz underlies all of existence, a background hum of probability and potential that never ceases. The particles that make up the solid world around us, and indeed our own bodies, emerge from and are sustained by this restless quantum substrate, which has no sound, no substance in the classical sense, yet is fundamental to the structure of reality. And in the slow transformation of coastlines, wave action gradually erodes rock and carries sediment along the shore, reshaping beaches and cliffs over decades and centuries. Waves are generated by wind blowing across the ocean surface, and they carry energy that can travel thousands of kilometers before finally breaking on a distant shore. When waves strike the coast, their energy is released, wearing away rock, tumbling stones into sand, and moving sediment along the beach in a process called longshore drift. The constant motion of waves sorts sediment by size, with larger pebbles and cobbles left higher on the beach and finer sand carried farther. Over time, this process can completely transform a coastline, cutting back cliffs, building spits and barrier islands, and filling in bays with sediment. The erosion happens grain by grain, wave by wave, in a rhythm that has continued for as long as there have been oceans and shores. Some coastlines erode rapidly, losing meters of land each year, while others are stable or even growing as sediment accumulates. The balance depends on the hardness of the rock, the strength of the waves, the supply of sediment, and the shape of the coast. Sea level rise and changing storm patterns can shift this balance, making coastal erosion one of the most visible signs of a changing climate. Yet even without human influence, coasts would continue to evolve, shaped by the silent, patient work of waves that never rest. The coastline you see today is just one moment in a long history of change, and it will look different in 100 years, reshaped by the same forces that have sculpted shores since the first oceans formed. And within the cells of plants, the process of photosynthesis quietly splits water molecules to release oxygen, a byproduct of the light reactions that power the synthesis of sugars. This splitting of water, called photolysis, happens in a protein complex called photosystem II, where light energy is used to strip electrons from water molecules. The oxygen atoms from two water molecules combine to form molecular oxygen, which is released into the atmosphere. This reaction is the source of nearly all the oxygen we breathe, and has been operating in plants, algae, and cyanobacteria for billions of years. The electrons stripped from water are passed through a series of proteins in the thylakoid membrane, generating energy that is stored in molecules of ADP and NADPH, which are then used in the Calvin cycle to build sugars from carbon dioxide. The entire process is exquisitely coordinated, with dozens of proteins working in concert, each performing its specific role in capturing and converting light energy. Photosystem 2 contains a cluster of 4 manganese atoms and 1 calcium atom, arranged in a precise geometry that catalyzes the water-splitting reaction. This cluster cycles through different oxidation states, accumulating the energy from 4 photons of light before it can split 2 water molecules and release 1 molecule of oxygen. The mechanism is so complex and efficient that scientists are still working to understand all its details, and it serves as inspiration for efforts to create artificial photosynthesis systems that could produce clean fuels from sunlight and water. All of this happens in silence, in the chloroplasts of every green leaf, billions upon billions of times per second, sustaining the oxygen-rich atmosphere that makes complex life possible. And in the deep history of Earth, the rise of oxygen in the atmosphere fundamentally transformed the planet in an event called the Great Oxidation Event, which occurred about 2.5 billion years ago. Before this time, Earth's atmosphere contained almost no free oxygen. It was composed mainly of nitrogen, carbon dioxide, methane, and other gases. Photosynthetic cyanobacteria had been producing oxygen for hundreds of millions of years, but the oxygen reacted with iron dissolved in the oceans and with volcanic gases, never accumulating in the air. Eventually, these oxygen sinks became saturated, and oxygen began to build up in the atmosphere, rising from near zero to perhaps a few percent of current levels over the course of tens of millions of years. This accumulation happened silently, without drama, yet it was one of the most consequential events in Earth's history. Oxygen is a reactive gas, and its presence made possible new forms of metabolism, including aerobic respiration, which extracts far more energy from food than anaerobic processes. This energy abundance likely paved the way for the evolution of complex, multicellular life. But the rise of oxygen was also catastrophic for many organisms that had evolved in an oxygen-free world, as oxygen was toxic to them. This has been called the oxygen catastrophe, a mass extinction of anaerobic microbes, though some survived in oxygen-free niches where their descendants still live today. The Great Oxidation Event also triggered a global glaciation, possibly the most severe ice age in Earth's history, because oxygen reacted with methane in the atmosphere, removing a potent greenhouse gas and causing temperatures to plummet. The planet may have been entirely frozen for millions of years, a snowball Earth from which it eventually recovered. All of this unfolded in silence, driven by the quiet metabolism of countless microbes, reshaping the planet and setting the stage for all the life that would follow. And in the formation of soil, the slow weathering of rock combines with the accumulation of organic matter to create the thin layer that supports terrestrial life. Soil formation, or pedogenesis, begins when rock is broken down by physical and chemical weathering into smaller particles. Water seeping into cracks freezes and expands, fracturing the rock. Acids from rain and from decaying organic matter dissolve minerals. Plant roots grow into crevices, widening them. Over time, rock becomes sand, silt, and clay, the mineral components of soil. Meanwhile, plants and other organisms live and die, and their remains are decomposed by bacteria and fungi, creating organic matter called humus, which gives soil its dark color and fertility. Earthworms and other soil creatures mix the mineral and organic components, creating structure in pore spaces that hold air and water. The process is extraordinarily slow. It can take hundreds to thousands of years to form just a few centimeters of soil, depending on the climate, the type of rock, and the vegetation. Yet this thin layer is essential providing anchorage and nutrients for plants, filtering and storing water, and hosting an astonishing diversity of life. A single handful of healthy soil contains billions of microorganisms, representing thousands of species. Soil is not a static substance, but a living system, constantly changing as minerals weather, organic matter decomposes, and organisms burrow and feed. It is also fragile, easily eroded by wind and water, especially when vegetation is removed. The silent creation of soil is one of the fundamental processes that makes land habitable, transforming barren rock into the foundation of ecosystems. And in the life cycle of stars, much more massive than the sun, the final stages involve the silent creation of heavy elements in the intense heat and pressure of the stellar core. As a massive star ages, it fuses hydrogen into helium, then helium into carbon and oxygen, then carbon into neon and magnesium, and so on, building heavier and heavier elements in a series of nuclear reactions. Each stage produces less energy and lasts for a shorter time, until finally the star has an iron core, surrounded by shells of lighter elements still undergoing fusion. Iron cannot be fused to release energy. Instead, fusing iron requires energy, so when the core becomes iron, fusion stops. Without the outward pressure from fusion to balance gravity, the core collapses catastrophically in less than a second, and the outer layers of the star rebound in a supernova explosion. In the extreme conditions of the collapse and explosion, elements heavier than iron are created, including gold, platinum, uranium, and all the other heavy elements. These elements are blasted into space, where they mix with interstellar gas and eventually become part of new stars, planets, and, in our case, living beings. Every atom of gold in a wedding ring, every atom of iodine in your thyroid, every atom of uranium in the Earth's crust was forged in the silent core of a dying star and scattered across the galaxy in a supernova. The creation of these elements happens in silence, in a vacuum of space, though the explosion itself releases more energy than the star emitted over its entire lifetime. The heavy elements are rare because they require such extreme conditions to form, and their presence in the solar system tells us that the material from which we formed was enriched by previous generations of stars that lived, died, and returned their ashes to the cosmos. And in the quiet depths of the ocean, hydrothermal vents release mineral-rich water heated by volcanic activity, creating oases of life in the otherwise sparse deep sea. These vents occur along mid-ocean ridges, where tectonic plates are pulling apart and magma rises close to the seafloor. Cold seawater seeps down through cracks in the rock, is heated to hundreds of degrees Celsius by the magma, and then rises back up, dissolving minerals from the rock as it goes. When this superheated water emerges from the seafloor and meets the cold ocean water, the dissolved minerals precipitate out, forming chimney-like structures that can grow meters tall. The water is often black with iron sulfide particles, giving these vents the name black smokers. Despite the extreme conditions, high temperature, high pressure, no sunlight, and water full of toxic chemicals, life thrives around these vents. Bacteria that can derive energy from the chemicals in the vent water, a process called chemosynthesis, form the base of the food web, and they are consumed by a variety of strange creatures found nowhere else on Earth. Giant tube worms, eyeless shrimp, white crabs, and many others. These ecosystems are entirely independent of sunlight, powered instead by the chemical energy of the Earth's interior. The discovery of hydrothermal vent communities in the late 1970s revolutionized our understanding of the limits of life and suggested that life might exist in similar environments on other worlds, such as the ocean beneath the ice of Jupiter's moon Europa. The vents themselves are silent, though the water they release is hot enough to boil if it were at the surface. They are windows into the deep processes of the planet, places where the interior and exterior of Earth meet and exchange energy and matter. And in the patient accumulation of ice in polar regions, snow falls year after year, and each layer is slowly compressed by the weight of the layers above, gradually transforming into glacial ice. The process begins with snowflakes, intricate crystals of ice that settle onto the surface and begin to compact. As more snow falls, the lower layers are compressed, and the air spaces between the crystals shrink. Over time, the snow becomes firn, a denser, granular form of ice, and eventually, under enough pressure, it becomes solid glacial ice, with the air trapped in tiny bubbles. This transformation can take decades to centuries, depending on the rate of snowfall and the temperature. The ice that forms in this way is a record of past climates, with each layer containing information about the temperature, atmospheric composition, and even the types of vegetation that existed when the snow fell. Scientists drill ice cores from glaciers and ice sheets, extracting cylinders of ice that can be several kilometers long, representing hundreds of thousands of years of climate history. By analyzing the ice, they can measure past levels of carbon dioxide and methane, detect volcanic eruptions from ash layers, and even identify changes in ocean circulation patterns. The oldest ice cores from Antarctica contain ice that is nearly 1 million years old, a frozen archive of Earth's climate history. The ice itself is silent, but it speaks volumes to those who know how to read it, telling stories of ice ages and warm periods, of volcanic winters and greenhouse climates, all recorded in the patient accumulation of snow transformed into ice. And in the behavior of light as it travels through different materials, it bends and slows in a phenomenon called refraction, which happens silently and governs much of how we see the world. When light passes from one transparent substance to another, such as from air into water or glass, its speed changes because light travels at different speeds in different materials. This change in speed causes the light to change direction, bending at the interface between the two substances. The amount of bending depends on the angle at which the light strikes the surface and on the refractive indices of the two materials. Refraction is why a straw in a glass of water appears bent at the surface, why lenses can focus light, and why rainbows form when sunlight passes through raindrops. The bending of light is also responsible for mirages, where layers of air at different temperatures have different refractive indices, causing light from the sky to bend and create the illusion of water on a hot road. Refraction is fundamental to optics, the science of light and vision, and it has been understood since ancient times, though the full explanation in terms of the wave nature of light came much later. Every time you look through a window, wear glasses, or use a camera, you are relying on the refraction of light, a silent process that redirects photons without altering their energy or color. The predictability of refraction allows us to design lenses and optical instruments with precision, shaping light to magnify, focus, or disperse it as needed. It is one of the simplest and most elegant phenomena in physics, a consequence of the wave nature of light and the electromagnetic properties of matter. And deep within the sun, nuclear fusion continues in a process that will sustain our star for billions of years to come, converting hydrogen into helium and releasing the energy that lights and warms our world. The core of the sun is unimaginably hot and dense, with temperatures around 15 million degrees Celsius and pressures so great that hydrogen nuclei are forced close enough together to overcome their electromagnetic repulsion and fuse. Each fusion reaction converts a tiny amount of mass into energy. According to Einstein's equation, E equals mc squared, and the sun converts about 4 million tons of mass into energy every second. This energy is released as high-energy gamma-ray photons, which begin a long journey outward from the core. The interior of the sun is so dense that photons are constantly absorbed and re-emitted by atoms, traveling only a tiny distance before being scattered in a random direction. This random walk means that a photon can take tens of thousands of years to travel from the core to the surface, even though the distance is only about 700,000 kilometers. By the time the energy reaches the surface, it has been transformed from gamma rays into the visible light and infrared radiation that we see and feel. The sun's fusion reactions are entirely silent, occurring in the vacuum of space, yet they're the ultimate source of nearly all energy on Earth, driving weather, ocean currents, photosynthesis, and the cycles of life. The sun has been shining steadily for about 4.5 billion years, and it will continue for another 5 billion or so, slowly brightening as it ages, until it exhausts its hydrogen fuel and begins the transformation into a red giant. For now, it remains a stable, life-giving star, powered by the silent alchemy of nuclear fusion. And in the quiet chemistry of your own body, enzymes catalyze thousands of different reactions, each one essential to life, speeding up processes that would otherwise take far too long to sustain a living organism. Enzymes are proteins that act as biological catalysts, lowering the activation energy needed for a reaction to occur and allowing it to happen millions of times faster than it would on its own. Each enzyme is specific to a particular reaction or type of reaction, with a shape that precisely fits the molecules it acts upon, called substrates. When a substrate binds to an enzyme's active site, the enzyme stabilizes the transition state of the reaction, making it easier for the reaction to proceed. Once the reaction is complete, the product is released, and the enzyme is free to catalyze another reaction. A single enzyme molecule can catalyze thousands or even millions of reactions per second, and your body contains thousands of different types of enzymes, each performing its specific task. Digestive enzymes break down food into molecules small enough to absorb. Metabolic enzymes build and break down the molecules that make up cells. DNA polymerases copy genetic information. The activity of enzymes is regulated in complex ways, ensuring that reactions happen when and where they are needed. Some enzymes require cofactors, small molecules, or metal ions that help them function. The study of enzymes, called enzymology, has revealed much about the chemistry of life and has led to countless applications in medicine, industry, and biotechnology. All of this catalytic activity happens in silence, a vast network of chemical transformations that keep you alive moment by moment without any conscious effort on your part. And in the slow movement of nutrients through ecosystems, elements like nitrogen, phosphorus, and carbon cycle from the environment into living organisms and back again, in processes that can take years, decades, or even millennia to complete. The nitrogen cycle, for example, involves the conversion of atmospheric nitrogen gas into forms that plants can use, a process called nitrogen fixation, carried out by certain bacteria in the soil and in root nodules of legumes. Plants absorb this fixed nitrogen and use it to build proteins and nucleic acids. When animals eat plants, the nitrogen is transferred up the food chain. When organisms die and decompose, or when animals excrete waste, the nitrogen is returned to the soil, where other bacteria convert it back into nitrogen gas, completing the cycle. The phosphorus cycle is slower, as phosphorus does not have a gaseous phase. It weathers slowly from rocks, is taken up by plants, passes through food webs, and is returned to the soil, eventually washing into the ocean where it can be locked away in sediments for millions of years before being uplifted by geological processes. The carbon cycle involves the exchange of carbon dioxide between the atmosphere, oceans, soil, and living organisms, driven by photosynthesis, respiration, decomposition, and geological processes. These cycles are fundamental to the functioning of ecosystems, ensuring that essential elements are available to support life. Human activities have significantly altered these cycles, particularly the carbon and nitrogen cycles, by burning fossil fuels, applying synthetic fertilizers, and clearing forests. Understanding these cycles and their disruption is essential to addressing environmental challenges. The movement of nutrients is silent and invisible, yet it is the foundation of all ecological systems, connecting the living and non-living components of the planet in an intricate web of exchange.